Welcome back, Physics 30. So this is FM2.3 mass and 2.4 Newton's second law of motion. So last day we looked at, or in the last video we looked at Newton's first law, the law of inertia, which means if an object is at rest, it wants to stay at rest. And so we have to put a force to get it moving. So that's referred to as inertia at rest. Or if an object is already in motion, moving at constant velocity, in order to change that straight line motion that it wants to have, we would have to apply a force. And inertia, of course, is an object's resistance to changing motion. So an object at rest wants to stay at rest, an object in motion wants to stay in motion, unless, of course, a force acts on it. So here we're looking at distinction between mass and weight. State Newton's second law, give an example that illustrates that. And identify the SI, or System International, metric system, units from force, mass, and acceleration. So if we look at mass and weight, mass is a property of an object. So the stuff that makes up an object contributes to its mass. If it is a measure of the amount of inertia of an object, so the amount of stuff. So for example, it's more difficult to get a car moving by pushing it than it is, let's say, a bicycle, because the car has more mass, that property that makes it difficult to start. Or if a car is coming towards us, it'd be much more difficult to stop a car than it would be, let's say, a bicycle, because again, it has more inertia due to a bigger mass. The more mass an object has, the greater the force needed to give it a particular acceleration, whether we want it to speed up or slow down if it's coming towards us. Whereas weight is really a force. Weight is technically a measure of force exerted on that object due to gravity. So due to being where it is, whether it's the Earth or the Moon or somewhere else, there's a downward force pulling the object down. That is technically weight. And that changes. That changes wherever you are. So this, we could say this changes depending upon location. So most of the time your weight is the same on the surface of the planet, and mass stays the same no matter where you are. So if you're on the moon, your weight is going to be less than it is here, but your mass is going to be the same. The amount of stuff that makes up you is going to be the same. So if you go to the moon, whose gravitational acceleration is about 1/6 g of what we have here, you will weigh much less. The force pulling you downwards towards the center of the planet, or moon, will be less, but your mass, the amount of stuff that makes up you, is the same. So Newton's second law. Newton's second law is the relation between acceleration and force. And we did a lab, of course, Newton's second law pertaining to this. The acceleration of an object is directly proportional to the net force. So the larger the force, the larger the acceleration. And inversely proportional to the object's mass. So if you have a larger mass, the force is less. And the direction of the acceleration is in the direction of the net force acting on the object. So that's a key thing to note as well. All right, so this law can be rearranged to be this. And of course, sigma is referred to as the sum of, or sometimes it's referred to just simply as, another way we can represent it as net. You'll see me representing it like this more often than not. And net is really the vector resultant force. I'll write the word vector there. So it's like the vector resultant force. Okay. So net F is a net force. It is in the unit of newtons. M is mass. It's in kilograms. And A is acceleration, meters per second squared. So what that tells us is that if F net equals MA, 1 Newton is equal to 1, so here we have kilogram, and A is meters per second squared. So it's kind of an awkward unit here to use, kilogram meters per second squared, but that's equivalent to a unit of force, which is 1 Newton. All right? So that is Newton's second law, basically this equation right here. So if we solve it for A, that becomes very similar to what you found out in the lab that you did. Oops. The larger the force, the larger the acceleration, and if I have a large mass moving, it has less acceleration. All right? So the force applied versus mass, larger the mass is, that something has to be pulled to lower the acceleration. All right, so if you look at the flip side here, force is a vector, of course. So F equals ma is true along each coordinate axis. The unit of force in the SI system is the Newton. Some other force units that have been used is Newton, dyne, pound, etc. But we'll stick to the Newton. Note that the pound is a unit of force, not of mass, and can therefore be equated to newtons but not to kilograms. So example, force to accelerate a fast car. So estimate the net force needed to accelerate a 1,000 kilogram car at a half g, and then what about a 200 gram apple at the same rate? Okay, so first of all, what we have to do here is figure out what half of a g is. Now a half of a g, a g is 9.80 meters per second squared, so of course that equals 4.90 meters per second squared. And then plug it into here, F net equals ma. So the net force being exerted on a 1,000 kg car to make it speed up at 4.90 meters per second every second, or 4.90 meters per second squared, that's going to give us a net force of 4,900 newtons. And of course there's 1 sig fig here, right? So if I was to round it off to 1 sig fig, this is a 9, so that 4 just simply gets bumped up by 1, 5,000 newtons. And B, going at the same rate, except this time it is an apple. That's 200 grams. So of course 200 grams, move the decimal 3 places to the left. Oops, I have one too many zeros there. 0.200 kgs. So if I use the same relationship here, so my mass of 0.200 multiplied by the same acceleration, and that's going to give me 0.98 newtons. And of course if we were to round it off to 1 sig fig, that works out to be 1 newton. And I technically should put a direction with both of these because they are vector quantities, right? So I'll just use the words forward here for direction. All right, let's look at another example. What average net force is required to bring a 1,500 kilogram car from a speed of 100 kilometers per hour within a distance of 55? Okay, so in this question we know quite a few things here. Key thing that sticks out here is our initial velocity. We know that our final velocity, let's see here, our final velocity is going to be 0 because we're bringing it to rest. And our initial velocity was 100 kilometers per hour. And of course we know if we divide by 3.6, we get that number in meters per second. In this case it's 27.8 meters per second. And what else do we know? We know the displacement this undergoes is 55 meters. And A is what we're looking for. How is the acceleration? Now, before we can figure this out, or actually, let's see here. We don't know acceleration, and yet we're asked to figure out net force. So if we take a look over here, F net equals ma, we need to figure out force at the end. We know the mass, but we don't know acceleration. So there must be a way to figure out acceleration. And if you look at your formula sheet, something that involves VF, VI, D, and A is this relationship right here. So we can use this to figure out A, and then from there we'll be able to figure out the net force by substituting it in. So we're bringing this car to rest. We were originally moving 27.8 squared, and 2 times A times 55. So if we subtract this, subtract 27.8 squared. I didn't work it out here yet. 27.8. So we're going to square this first and then subtract it. Oops. 27.8 all squared plus 2 times 55 is 110. So divide by 110, divide by 110, and I think A works out to be negative 7.0 meters per second squared. Okay, so just rearranging this equation to solve for A, that's what we get. And it makes sense that it's negative, right? Because we're slowing down in the direction of motion. So if this is the positive direction, to be slowing down in that direction, our A must be negative, working against the movement. So F net equals, let's see, mass, the car is 1,500 kgs, multiplied by an acceleration of negative 7. So the net force works out to be negative 10,521 newtons. And I think if we round that off to, I think I rounded off to 2 sig figs. Ideally, maybe I should have rounded off to 1 sig fig. F net is equal to, maybe I will round it off to 1 sig fig. So this is a 0, so this is going to stay as a 0, or sorry, as a 1. So I can say negative 10,000 newtons is what we get. All right, so yes, we may have to use some relationships from the last unit to apply them into here. All right, so that's it. You should be able to do the assignment. It's not too bad, and we'll see you again.